Greetings, let's answer a simple question, which is not as general as the general theorem, but it is that if we have a cycle graph, which basically means put vertices in a loop like this, make a simple graph like this, vertices, a simple graph like this in this cycle manner. You have n edges, n vertices for Cn. That means free vertices, free edges for C3. Can you separate out the vertices of this graph in such a way that you will separate them into two subsets that together give all the vertices, and within each of those two subsets, the vertices have no edges connecting them to each other, but there can be edges connecting them to the vertices of the other set? Well, it won't happen with C3. Because if you choose any vertex, C3 is actually at the same time a complete graph. So that's a very trivial way to reason this out. Any vertex you choose, it has edges to both the other vertices. So you cannot find such a set. Let's see for C4. Is it bipartite? Well, let's see. So C4 is looking like this, which means 4 vertices, 4 edges. Just like before, we're 3 vertices, 3 edges. Now we can do what was mentioned, that namely means find a subset that would be these 2 vertices, for example, such that they are not connected to each other by any edge, but that the rest of the vertices in the graph, the other subset, because automatically we broke up this Cn, this C4 in this case, into 2 subsets. The 2 vertices that were circled and the 2 of them that were not circled. And both of them fulfill that within that set. They are not connected directly by any edge, just like the circled ones, but they are connected by edges to the other subset, which means from the circled ones to the non-circled ones, and vice versa. So this is a general thing, and there's a theorem for this for all graphs, and that states a graph is bipartite if and only if it has no odd cycles. And this is a very simple case of it when you have a cycle graph, because cycle graph means it's a cycle you can have within any graph that's more complicated, but the cycle graph is purely composed of a cycle, so that's all there is. So if it cannot contain any odd cycles to be bipartite, and then it's guaranteed to be bipartite, that means that once we have a cycle graph, all we need to verify is the number of vertices. So if we have a cycle graph like this, as long as it has an even number of vertices, it's bipartite. So we saw it here demonstrated for C3, C4. But now let's see about, for example, C5, and then let's wrap it up with C8 as examples. So that theorem is more general, that was mentioned, and we're not doing any proof. We're just looking at the concrete cases and verifying this observation. So C5, we have 5 vertices and 5 edges between them. Can we do the similar thing? What we did is always took one. We could start with anything if we are talking about the circled set. Choose, for example, this one, then skip one, then take the third one, and then skip one, but now we're back. So now it's more vertices. So let's choose one, any, just like before. It didn't matter where we started because it's highly symmetrical in this cycle way. Then skip one, go to next one, then skip one, but then we would skip to a vertex because we're now looking for a subset of those circled ones. Well, then if we skip another one, we're next to a circled one, so we cannot do that. That's sort of a contradiction. We want a subset of those that are circled that don't have any edges between each other. But that happens as long as the circled are like this. But then the remaining ones that are not circled must also not have any edges between each other. But that doesn't happen because these two do have an edge. And if we circled one of these two, then the circled ones would have an edge between each other. So both ways it wouldn't work. So C6 should work because it has an even number of vertices. C7 again should not work, and C8 as an even graph it should work. So let's wrap it up with this example. So let's take C8. That looks something like this. It doesn't matter exactly how one draws it. So C8. And all we do is, again, we can start the same way like before. Circle any of them, skip one, circle the 1, 2 away from it, and continue and see if it works out. Because that's the way how we can separate up a cycle graph. Where it works, we always have one space between the circled ones, so they have no edges connecting the circled ones, and the non-circled ones also have no edges connecting them to each other. So it works out. This is again a bipartite graph. So just like that theorem generalized for all graphs, here we have that a cycle graph is by the same condition, because it's a simple case of a more general rule. A cycle graph is bipartite if and only if the number of the n here, the c, because it's in general Cn, the number of vertices is even.